Thank you very much. Yeah, it's a pleasure to be here. It's a pleasure to give this talk here in this audience, in front of this audience, and at this place. Of course, there are many experts here that I'm happy to talk in front of these experts about these topics. Also, I'm happy to talk about this because Elon and I had these ideas that I want to present in this building about 2 years ago. And finally, I'm allowed to talk about it. And also, I'm happy that somehow the intersection of the experts maybe uniquely, or not quite, but maybe uniquely characterizes Hillel here. So I'm happy to be here at this occasion. Right. And if the organizers are organizing a prize for the longest title, I want to put myself into the contenders. Right, so what I want to talk about, of course, starts with a theorem of Fürstenberg. '67, most of you know it, but let me remind you for those that haven't seen it. If A is a closed subset of the circle group T equals R mod C, and it's invariant under times 2 and times 3, other primes or other coprime numbers would work too. And then we get a conclusion. Either it's a finite set consisting of rationals, or it's everything. And of course that started the question, because we are interested in topological dynamics, but we're also interested in ergodic theory, so maybe there's an analog to that in the ergodic theory world. So the question would be, and that's a conjecture of Fürstenberg, or a question of Fürstenberg, suppose you have a measure that's invariant under times 2 and times 3, it's on the circle group, it's ergodic, just so that we are in the right setting. Do we then know what it is? Is it then either a counting measure supported on finally many rational numbers which form a periodic orbit for times 2 times 3, or the Lebesgue measure? That's an important and interesting question. Still, it's still a question today. What we do know is partial results. It started with Russ-Lyons, and maybe the most satisfying result towards the question is by Rudolph. Suppose mu is times 2 times 3 invariant and ergodic, as I said before. Probability measure on the torus. And we need an extra condition. Say entropy of times 2 is positive, or entropy of times 3 is positive, or times 6, or it doesn't matter which one you prefer to assume has positive entropy. Then it's the Lebesgue measure. And somehow this started the whole area, because you can ask that question and you can ask that question in other situations. And Behrendt generalized this theorem to the torus. So Behrendt for actions on T to the n, or also solenoids later. And also this question got refined, got generalized. And then there are many names. I don't want to give you all the theorems that sort of go into this, because I would probably fill the hour using just that. But let me give you some names so that we see the history developing. So Katak and Spazier had a paper for the torus and some special results on G mod gamma. But there were extra conditions somehow. So not just positive entropy, but more ergodicity somehow, some kind of maybe mixing properties or something like that for the measure. Then the method worked. Kalinin joined Katak and Spazier a bit later. Again, the story became a bit nicer, but still there were extra conditions, either on the action or on the measure. So it was kind of special still. Then I came to Penn State, and I had a paper with Anatol Katok. That was the first theorem, maybe in G mod gamma, where there was no condition other than an entropy condition. But we needed quite a lot of entropy. And positive entropy was not sufficient. We needed lots of entropy, sort of more than 1/2 of entropy. And today we call this the high entropy method for that reason. And around the time, Elon worked on the quantum unique electricity problem and was able to give a theorem of that sort for quotients of SL2, where the high entropy method just stops working, it's completely useless. So the high entropy is sort of, it's a bit local in the argument, and it means SL3 or bigger somehow. SL2 never will work with high entropy. And Elon had a new method, another method that also works for SL2R, say SL2R cross SL2R, so that we are in the higher rank situation. We need always two maps, right? If you have one map, there's never a theorem like that, because we are not in the unipotent world. We have diagonalizable elements. We sort of hyperbolic behavior of a single map. But we have two of them, and they're really very different. Here they are coprime, and in SL3R, they are, well, you have a two-parameter subgroup in SL3R. So you can study those two directions, and you're sort of in a similar situation. Yes. For the torus, Elon and I had some time ago a complete understanding, torus and solenoids. But somehow we never got to a situation where we had one method that worked in all of these scenarios. We had the high entropy method and the low entropy method, and we generalized them to the maximal situation, and we had quite a few papers on the topic. Joinings, for instance. Joinings is a wonderful topic. Joinings, for instance, we can classify in any G mod gamma situation. So that's the current situation somehow. The joinings theorem and maximal diagonal actions, they always work. Right, that was the situation essentially 2 years ago. So let me again make some space and then present the new ideas and the new theorem that we can now prove. If you have questions, speak up. If that's your choice. Such a beautiful title, but it wastes quite a bit of space. Right, so what's the theorem? I was saying SL2 cross SL2, Elon could do some time ago. But this method does not work if you take SL2 cross SL2 cross SL2 and then a two-parameter diagonal subgroup. So let's take SL2 to R to the K mod gamma, K greater equal 2, and even for the case K equal 2 is already covered by Elon's paper. And let's say gamma is irreducible. If it's reducible, then either you are sort of having a rank 1 picture in there, and if you don't have a rank 1 picture there, then you have a joining. But joinings we already understand, so we can reduce it to the irreducible case. A is sort of a, so our A is a subgroup of A max, and A max is just diagonal subgroup to the K, and our A is two-dimensional. Mu is A invariant and ergodic. Entropy is assumed to be positive for some A in A. So those are always the type of assumptions. I want at least two directions so that I'm staying away from the anoss of the hyperbolic world. And I need an invariant and ergodic probability measure and positive entropy. Yeah, it would be great to have this assumption not, but yeah, this is what we know how to do. And now more generally. Then, so what's the conclusion? If X is compact, mu is a Haar measure on an orbit. If X is compact or K equals 2, right? Because for K equals 2, Elon already gave us the statement anyway. But our method also handles the case K equals 2, and in that case there's no other possibility. If X is not compact, either that, of course we are happy if this happens, or mu is invariant and under a unipotent flow, and mu is supported on the normalizer on an orbit of the normalizer of this group.
This group is the unipotent group?
Yes. So let me give you an example. Say K is a cubic number field, and you take the ring of integers within this K, and you take, and it's totally real, and you take SL2 R cubed mod SL2 O. It would be nice to just write C square root 2, but then I don't have three places. And for two places, this example doesn't appear, so yeah. But never mind, let's do that, because it's much easier to understand what's going on if I do that. So X equals SL2 R squared mod SL2 C bracket square root 2 is my space. And then I can have the unipotent group, which is the upper unipotent cross the upper unipotent. That has a closed orbit on this quotient. It's easy to see. And you can have a closed finite volume. I mean, it's if you take U gamma, this is just isomorphic to the 2 torus. And on the 2 torus, you have the matrix 1, 2, 1, 1 maybe. Maybe the square of that, because the determinant might be -1 if I'm mistaken. That's sort of a matrix that uses square root 2 inside it. So I can have the dynamics of this 2 by 2 matrix on the 2 torus, and I can see it somehow inside the space, because this, if I write it differently, becomes an element of the lattice. And then I have this two parameter torus and a suspension flow over it. If I do this with a cubic number field, I can have a 3-dimensional torus with two diagonalizable maps acting on it, and I can do the suspension flow over it, and I see this within my space. And this possibility can only occur if the unipotents can have closed orbits, and unipotents can only have closed orbits when the quotient is non-compact. So that's somehow how the torus can fit inside my space. If I take SL2, then this doesn't appear at all because I have only one unit, but I have a two-parameter diagonal flow, and the other part of the flow would just go to infinity. And that means that the other direction doesn't have recurrence, hence there's no invariant measure of that sort for the full two-parameter group. But in SL3, I have two units, I have a two-parameter group that goes with it, and then I can have this picture. And if I go to SL2 to the k, then I can do some other number field, but nobody's telling me that the units that I use are really generating this number field. And because of that, the conclusion is somehow weaker than what I would like to have. But I can't avoid it because if there's a zero entropy measure that is continuous and zero entropy for some of these torus examples, I can hide it inside this space. So if I would be able to say here more than what I say, I would solve the problem of Fürstenberg completely independent of an entropy assumption. So this is the only thing I can say, assuming just positive entropy and no more precise assumption about the geometry of A inside SL2 R to the K. If this is sort of very generic or something, then I probably can say more, but yeah. Right, this is the theorem. We also have a version of SL3. Maybe I do the changes here. I take SL3 squared, modern irreducible lattice. I have a particular diagonal subgroup in mind. It's two-dimensional. I have an invariant measure that I assume exists with positive entropy for some element. I need to rephrase the conclusion. So one possibility is definitely we use a H measure on an orbit. That's a good possibility. Of course, I like that. And for certain lattices, this will be the only conclusion. One possibility is that mu is invariant under a unipotent flow and mu is supported on an orbit of this unipotent group. Again, just as before. But another option is neither of the three, and that's mu is supported on an orbit of, say, SL2R squared times the diagonal group. Somehow this A that I have here, it doesn't fit inside SL2. If I say, think of SL2 here in the lower corner and here in the upper corner. You could have an SL2 squared that inside SL3 squared sits like this. Then this A that I see is not the A inside the SL2, and it's not commuting with the SL2 that I have here. So if I have some entropy, then somehow these unipotent directions can give me entropy even on SL2. But over here, the element that commutes actually with the SL2. And I mean, the key word that goes with this type of example is Rie's type example, because she came up with these type of counterexamples to a very optimistic conjecture of that sort for G mod gamma. And basically what I'm saying is I have some big 16-dimensional space, and inside the 16-dimensional space I have sometimes the pictures look like this. I have an SL2, and then I have an attached other direction that just closes up and doesn't do anything. And in that case, even for its higher rank, it's basically rank 1. I can't prove anything about the measure rigidity. And yes, in my example over here, it's not really SL2, it's SL2 cross SL2, but I only have the diagonal element here in the first copy. So I have a one parameter inside this one, and then I have an extra direction that doesn't do anything. And in this scenario, positive entropy will not help me to say anything. The measure can be fractal. No conclusion is possible. But what's the conclusion of the theorem is, either it's a nice thing or a semi-nice thing, or, well, I'm really stuck on an orbit where it's clear that I cannot say anything else. So maybe this is to be taken with a grain of salt. It's not really written up yet. Maybe the correct number here is 2016. Yeah. The SL2 I have written down already, and SL3 comes afterwards, yes. Are there any questions at this point? Otherwise I need to hurry up and get to the other parts of the title. This theorem is for A of this type. We probably could work a bit harder and do other cases, but with what we are currently doing, we can't do all cases. And this case is an interesting case, because if you are interested in applications, somehow this case often comes up. So a general diagonal group somehow is less interesting from the application point of view than this one. So we were particularly interested in this one, and up to 2 years ago we were quite annoyed that we couldn't do this one. And now we can do this one, so we do it. I also should say that maybe one difference to earlier arguments is that we start using Diophantine approximation much earlier in the game. So I didn't say, but I should have said, that all the gammas that I use are arithmetic lattices. So irreducible and arithmetic. In both theorems, this is an assumption. Yeah, it's a corollary anyway from someone else, but yeah. I need that input to get started. There's rigidity, right? So, yes. Good. So let's go and start thinking about the proof. Well, in ergodic theory, very, very often, we use conditional measures. Every time one talks about factors, one talks about conditional measures. And if you do a symbolic space, for instance, with any kind of invariant measure for the shift map, then you immediately see that entropy is related to conditional measures as well. For the times 2 map, entropy is related to the conditional measure of the sigma algebra, which is the preimage of the Borel sigma algebra of the times 2 map. And that sigma algebra is always has atoms that consist of 2 points, x and x plus 1/2. And then maybe the conditional measure is trivial and sits on only one of the 2 points. And if this happens all the time, then you have 0 entropy. And maybe sometimes at least it doesn't sit only at one point. It sort of gives you a distribution on these 2 points. And it has really both points in the support of the conditional measure. If that happens, you have positive entropy. And you can phrase that statement in terms of a two-adic foliation of the invertible extension of the torus under the times 2 map. My spaces that are presented, they are not quite, they don't have the p-adics there, even though the theorems are true in that generality. Also, so I need some replacement of that condition, of that relationship between entropy and conditional measure. And this has been worked out in many contexts, and we call them Leafwise measures. And it's basically the same idea as what I said, but it's more work to get everything out of the discussion. So I have x, and for little x in x, I get a measure on u, on u, and this u is a unipotent subgroup. It's actually the horosphere for an element A, horospherical subgroup, I should say. So what do I mean by that? U is equal to Ga minus. It consists of all elements that when I contract them, conjugate them with my acting element, this conjugation converges to the identity. So in the SL2 case, and I can use the diagonal element e to the minus 1, and then the u that goes with it would be, I could be wrong, but okay, maybe it's this one. There are two choices, so it's not so difficult. So what I'm saying is, if you take the geodesic flow on the model surface or on some other quotient of SL2, then entropy of that map for an invariant measure on the quotient is related to the behavior of the measure with respect to this group U. But of course, this group U, a priori, we don't know anything about this group U and the measure. There's no invariance, no quasi-invariance, there's nothing. There's only the statement that there are typical points on U orbits if you have positive entropy. And there are at least two, but then there are always many typical points on typical U orbits. And this is captured by this measure. And this measure is a nice measure on U, nice meaning locally finite, and it describes this distribution of the typical points on the U orbit as viewed from the point X. So I don't know how meaningful it is. I can draw some picture. I have here X, and then I have the U orbit, and the U orbit does something. It might return, it might do other things, and the measure is kind of some patchy thing that is invariant under A and sometimes intersects with this orbit. But of course it's a measure, it's not a set, so this intersection is not a set. This intersection is again a measure, and one can make sense of all of this. But again, it would take some time to do this. So let me just say that this is a fancy generalization of this statement that I had before. If you have positive entropy for times 2, then somewhere in the space you have tuples of points x and x plus 1/2 that have similar probabilities somehow. I mean, where not only one of them is likely to happen. And this is working also in the general context. So positive entropy is equivalent to this Leafwise measure not being equal to the Dirac measure at the identity almost everywhere. If it's trivial, this is called trivial. If it's trivial almost everywhere, then you have zero entropy. So it's not all the time trivial. But then ergodicity kicks in, and if it's non-trivial at some point, it's non-trivial everywhere. And more things. So if you have positive entropy, then you have some number which it is. And then you actually get more statements out of this. You get, if you look at the measure of the expanded ball. So I take the one ball in the group, and I go the other direction because I said U is defined by going to the identity. Go the other direction. So the one ball doesn't get smaller, the one ball gets bigger. I take the measure of that, take the logarithm of that. Well, we're talking about entropy, so I always have to take the logarithm, right? Divided by n. That will be the alpha, almost surely. So this Leafwise measure that I constructed in some mysterious way not only tells me whether I have positive entropy, it also tells me the entropy. And this is just an ergodic theorem. I mean, if you can set up the correct function, sample this function along an orbit, and out comes the statement. And the correct statement is you need to take you expand the one ball once and take the ratio of the measure of the expanded ball by the ratio of the one ball divided by the measure of the one ball. Take the logarithm of that, now apply the ergodic theorem. Out comes this. If you average in the other direction, you're supposed to get the same answer, right? If you average in the other direction, then you shrink. So you get the same statement whether you shrink down to the identity or whether you expand to get bigger and bigger balls. So that's something that we will need to use. Okay. Elon proved in his paper on quantum uniqueity the following theorem. If mu x u is equal to infinity, then we have recurrence under u. Poincaré recurrence under u. And it's a funny statement because we don't know that the measure preserves, that the group U preserves the measure. It's a very abstract theorem, but the information that you need to know is sort of in the Leafwise measure. Okay, so we have recurrence now that enters the picture. Elon was interested in this theorem not for U, but for a different group, different foliation somehow. And one of the new aspects is that we want to study this precisely for the unipotent group. Now, Boschanitsyn has a paper, very nice paper, where he says Poincaré recurrence is not just an almost everywhere statement that at some point you return. No, much more is true. If your space is finite dimensional, then almost every point will have a certain speed at which it returns. So it's a quantitative statement. Now, of course, we have a quantitative statement regarding this infinite measure here. We have finite dimension, of course. So one should be able to combine these two thoughts, and one is able to combine this and get the following theorem. So that's now part of the 2016 paper. Under this assumption, so mu is A invariant, positive entropy, then almost every point has the property that for large enough there are U returns within the expanded ball. So I take this unipotent group, I the one ball in there expanded by my flow. It's a large exponentially growing thing. And within this, I return to a small neighborhood around the identity, around the point that I started. And I can return to an exponentially shrinking ball around that point, where kappa is equal to kappa alpha dimension g is of course positive, but it exists. So what do I mean by that? If you have a point x in the space, the group is continuous, right? Of course there are very close by points that are also in the set. But those are stupid, they are not returns. I mean, I've been there, right? I am there, I'm in the set now. So I'm not interested in that. I need to go out away from that point, at least by distance 1. And after I've gone out the distance 1 or the injectivity radius of the point, and then come back, this is what I call a return. And almost surely, for every large enough time, I have this return. And basically, it's a quantification of this theorem of Elon's, plus the knowledge that I have this exponential growth rate of the measure of the ball, and Borel-Candelli. That's what I need to do, and then I get this out of it. I can also do this a bit better. I can take here e to the alpha over n, many returns. Again, what are many returns? What does it mean to have n returns within this? Alpha over 2, sorry. Alpha over 2 times n. Sorry, yes, and exponentially many returns. Then the kappa gets down, but it's okay. So I have multiple recurrence. I come back not once to this exponentially shrinking thing. I come back exponentially many times within the shrinking thing. In some sense, I keep saying exponentially, but I could also say polynomial, because I have an exponentially shrinking ball and an exponentially shrinking radius. So of course, if I phrase something in terms of the radius of this, I could say it's a polynomial statement where the degree of the polynomial, the kappa here, depends on the alpha that I started with and the dimension of the group. Okay? So far, okay, it's a nice statement. What do we do with it? Are there any questions to this statement so far?
You wanted to take nicely increasing.
Yes.
Attribute.
Yes. No, this is increasing because U is stable.
Yeah.
I said it wrong, but I wrote it correctly. Okay. Thank you.
So what happens to all of every point in terms of the recurrence rate? And how does this compare to the ultimate? Not with respect to mu, just
With respect to the H measure?
yeah.
I guess with the H measure you can then figure out the correct kappa. I mean, what I have is an alpha that's not the maximal alpha. And this kappa is alpha divided by the dimension and a bit smaller than that so that I can use Borel-Candelli, something like that.
Your kappa is an explicit number or something?
Yes, yeah, I just told you. Alpha divided by the dimension, minus a bit so that I can use Borel-Candelli. Yeah. Need to check, but that's what I would say right now. Okay, so there's no higher rank in this theorem. It's just, okay, I have multiple recurrence and I have exponentially many in a direction that doesn't even preserve the measure, but okay, that's a statement.
So how is this different from what Alon already proved? That because of this rate, right?
The rate, yes. So I have a shrinking thing. Yes. Yes. But that's just Borel-Candelli. But somehow it wasn't a difficult thing to prove. It was difficult to realize that it's useful. So let me tell you why it's useful.
Points get together.
Yeah. So let's talk about the particular case. SL2, well, I could say 20, but that's too difficult to write down. SL2 cross SL2 cross SL2 cross SL2. And then I have an A, which is E minus 1, E minus 1. Identity, that's my first element. B is identity, E minus 1, whatever, I don't care. Okay, that's my higher rank situation. I have an irreducible gamma. I have a measure that's invariant under both of these transformations.
The question mark was what?
Identity or this, or the square of this. Up to you to decide. Take the identity. If h mu of A is positive, then h mu of B is positive. B is the other element. So a priori there's no connection between the two. This guy is doing stuff from these two groups, and the U that I defined is some unipotent group in here, and this guy is doing something here, of course commutes with the other one, but in terms of obvious information, this is not obvious. If I take AB, the product of A with B, then it's obvious that this has positive entropy. It would have entropy of A plus entropy of B. But this is relying on the assumption that gamma is irreducible and on the phantom information in some funny way. So let's assume the opposite. Assume entropy h mu of B is equal to 0. Let dn, d kappa n, denote the Bowen ball for B up to kappa n. Floor, ceiling, who cares?
Gamma is co-compact, not co-compact?
I don't care right now. Compact, because at some point they say cover, but you could have complained about this earlier, right? So, yeah. But if I don't cover everything, I cover 1 minus epsilon, and I don't see any difference between the arguments. So what do I know about the Bowen balls? They're defined by B. B has entropy 0. So the rate at which the Bowen ball shrinks is basically 0, because that's the entropy of B. So if I take the measure of x d kappa n log divide by n, put the minus in front so that I get a positive number, because this shrinks now, take the limit, this is equal to 0. 0 equals the entropy.
Bowen ball around some point.
Yeah, so this is defined in the group around the identity, and then I push it down to the point in this way. It's really good to have experts in the audience, yes. Then I say the right things. So I can try to do what I said before. Before I said, let's just cover the space by balls. And if the radius is small, I know how many balls I need to cover the space. But there I use the dimension of the space. I said the dimension is finite, hence I have some information on how many balls I need if the radius is whatever it is. I want to do the same thing, but now with the Bowen balls. But the Bowen balls are basically not shrinking in measure. Everything is measured in terms of this exponential scale. The exponential scale is saying this is not shrinking. So I need very few Bowen balls to cover the whole space. Right? So I get the recurrence statement as before. To the exponentially shrinking Bowen balls, mu almost every x satisfies for large enough n that there are e to the alpha over 2 times n many u returns within a to the minus n b1u a to the n 2 x d kappa n. And of course, for large enough, that's sort of what the Borel-Candelli tells me. You see the Borel-Candelli sort of in the statement, if you think about it.
That's U for A?
What?
That's U for A?
Yes, the U I define for A. This is for A, but this is for B. Thanks for the question. It's a bit confusing what I do, but this is what I want to do. And here's the big difference. For any kappa bigger than 0, e.g. 10 to the 100. Because entropy is 0, no matter what I do with the kappa. If I set kappa 10 to the 100, it's still true that this converges to 0, because I multiplied this by 10 to the 100. This is a ridiculous statement. Because this Bohren ball is a thin neighborhood of the diagonal A max in the second two, or in the third copy, maybe in the second and the third and the fourth, and then the one wall in the first two. But it's an irreducible lattice, right? Whatever is going on at one place is going on everywhere. It's somehow, because it's an irreducible lattice. So why is the lattice now back in the picture? What does it mean to return? I have an x, I hit it with a u, I get an x, and then I have an epsilon. And this is an element of the shrinking Bohren ball. But of course, if I get rid of, oh sorry, the talk so far was with gamma on the left, on the right. So at some point I get confused because I made this choice. Never mind. So u g gamma is equal to epsilon g. That's what this statement means in the group. Epsilon is in the Bohren ball. So u is unknown, not completely. I know have some control on the size of u, but it's kind of large in the first two copies of the SL2 was SL2 was SL2. This guy in the third copy is super close to the diagonal element, where this u is trivial anyway. So everything is conjugated by the g, but what I get is that the gamma is very close to A in the third copy of SL2. Suppose you have two such guys. You have a gamma 1 and a gamma 2, because I said you have exponentially many returns, right? Suppose you have two such guys. Take the commutator of the gammas. Then this is very close to the identity, because A is commutative. But it's so close to the identity that it's a contradiction. It needs to be the identity, because the gamma consists of algebraic numbers, and the heights of the algebraic number is controlled by the size of u, which is controlled by the a to the minus n b1 u a to the n. I know how big the u is in the first two copies. In the third and the fourth, the u is not existent. The epsilon is bounded, and in one place, it's super small. That means the commutator is, and that means that the commutator is the identity. So I'm saying something like if m plus square root 2n is less than 1 over max mn to the 10 to the 10, 3 would work, I guess, or something, then m and n is equal to 0. I'm saying something of that order. And that's because I could choose the kappa now. I could choose the kappa as I wanted, and I can choose it so that I get inequalities, if there are phantom inequalities that are ridiculous. So I get many gammas that actually commute with each other. And they are very close to the diagonal group. If they are that close to the diagonal group, they are diagonalizable. But actually that can't be. You can't have that many diagonalizable elements from the same diagonal subgroup, exponentially many, up to that height of the gammas that you're looking at. So you get a contradiction, and you have shown that this cannot happen. You must have positive entropy. Okay, so this is nice. Okay, what do we do with it? So what I'm saying is, this was a very nice conversation with Elon down the hall, and we were quite confused by this for 5 minutes or so, and it kept being confusing, but in a nice way, because this is basically the end of the proof. Now we are done, and we have unipotent invariance. You don't see it yet, but since we have unipotent invariance, we can rely on Marina's works, and yes. So why is it giving you invariance? This argument can be done conditionally on the factor defined by x goes to a Leafwise measure, but this time I look at the Leafwise measure for the holosphere of B. So this is GB minus. That defines a factor, a measurable factor. And when I go from x to ux, as I do here, that's what I use to get my positive entropy statement. When I go from x to ux, I'm not changing the Leafwise measure of the other copy. And that's part of the high entropy method. We call it the product lemma for conditional measures. In this situation where sort of one space has nothing to do with the other space, the unipotent groups commute, you can contract one and not the other, or the other way around, and then you just need to use Hopf's argument for ergodicity in the correct way, and you get a product structure for the Leafwise measures. So if you go along U, which is the U in the first two copies, you're not changing the Leafwise measure for the third and the fourth copy, which means you're staying in the same fiber for this factor map. And by doing everything sort of over this factor map, we show that we have conditional positive entropy. But I said earlier, what does positive entropy mean? Positive entropy means that you have 2 points on the same Horus cycle that are both typical. Now we have this conditionally. So we have 2 points on the same Horus cycle, which is this orbit, that are also on the same fiber for this factor map. But these Leafwise measures, they always view the orbit from the point. So you have that this orbit of this unipotent group from that point looks the same way as from that point. That's a translation invariance. And it's a unipotent translation invariance, so we can go home. Thank you.
Thank you, Manfred. To whom can I give the microphone to pose a question? Just a second.
Short question.
But you speak the question to the microphone.
Well, just one word question. Did you say applications of this SL3?
Yeah, so what we are hoping to get with this SL3 case, which is more interesting because the Born ball is a different shape, and that's why it's trickier and you get more cases. what we're hoping to get is a generalization of this theorem of Elon, Akshay, Philippe Michel, and myself, where we had, if you start with cubic number fields, but you assume that they are totally real, you construct the order in that number field, and you construct the ideal classes. And the ideal classes give you periodic orbits in SL3R model SL3Z. And they are A, capital A, being the maximal diagonal subgroup in periodic orbits for the two-parameter diagonal subgroup. And there we relied on the paper with Katok, where we joined forces with Elon and classified really all the A invariant measures with positive entropy for this quotient. And the statement here is that they equidistribute. These equidistribute if one varies the field. So it's an arithmetic ordering of the periodic orbits of capital A, and it's a much finer collection than saying everything up to a particular volume. But even that statement, I'm not sure whether you can get that without relying to this theorem. And it has an assumption. Well, it has an assumption that we're talking about cubic fields. Okay, it's the next case after 2, and 2 has been done by Duke. So it's a good case, but it has this other assumption, totally real. And that totally real gives us the full diagonal subgroup, which makes us able to cite the paper with Katok. Okay, if you now take, say, a different ground field, L, and you take a cubic number field over L, and L is a number field over Q, but it's not equal, then, okay, maybe you're lucky and in one of the places over L the K is split. Then you can again cite the paper with Katok. But if not, then you run into precisely this picture that I had on the board. So we are hoping that this is now a corollary of that paper plus, again, the number theoretic L function input. But that's sort of maybe not 2016. Yeah.
Would anyone else like to enjoy the microphone? If not, let's thank the speaker.
Thank you.